welcome you all to the online NPTEL course on smart grid. Today we will be focusing on a case study with respect to AC/DC smart grid, and we will try to take up an application where we will try to explore the benefit of having a AC/DC smart grid so that the main objective here is to highlight the advantage of a AC/DC hybrid grid against the conventional AC grid. So, in this context we will take up a case study, that is coordinated voltage control scheme applications, and we will see how this coordinated voltage control or CVC scheme can be adapted well with our AC/DC hybrid grid instead of a conventional AC grid. And perhaps we will take advantage of the presence of a DC grid, DC microgrid along with a AC distribution system. Now, first of all, what is voltage regulation, or voltage control, and what are those devices, what kind of schemes are in practice, and during different state of operation how do they react, and what sort of modification or improvement is being expected looking into a merger of AC/DC smart grid. Now, first of all, if you concentrate on voltage regulating devices, we can just focus on OLTC, D-STATCOM and all the converters connected to my renewable energy systems. Now, if you focus on coordinated voltage control or CVC scheme, the main objective of the CVC is to optimally utilize different compensating device to increase reactive power reserve. Means the objective here is how to increase the reactive power available within the system to take care of the voltage control. Now, meantime we can also try to achieve the post fault voltage recovery time can be reduced as soon as possible. Maybe the post fault voltage recovery time can be reduced with the help of CVC scheme. Now, there are two major type of CVC, one is decentralized and the other one is centralized. Centralized where we have communication system in place, decentralized where we do not have any communication among the devices. Now, focusing on a simple test system, so we have considered IEEE 33 bus distribution system which is as conventional you can see. Whereas we have connected a DC microgrid, at a particular bus number 5, and this is the bus where we have connected a DC microgrid, and we also have connected a D-STATCOM at bus number 22, and we also have connected a DFIG at bus number 22. And we do have a OLTC at bus number 1. So, what are the major changes we have incorporated? We have taken a IEEE 33 bus system and we introduced OLTC at bus number 1, D-STATCOM as well as DFIG wind generator at bus number 22, and at bus number 5 we have introduced a DC microgrid. So, excluding all those devices and the rating, the rest loading and the dimension as well as the variables, so the parameters of the lines and cables remain same as per the IEEE system. Now, voltage regulating devices like OLTC, D-STATCOM etc. as well as DFIG converters are operated in a decentralized manner. That means, all this system, if you see, all the devices do operate without any communication. Means those devices do try to improve the voltage profile at that particular bus where it has been connected through different schemes, but they do not communicate to each other for the overall system benefit at large. and hence they perhaps regulate the voltages in their own way at the respective buses, but they do not look at other buses. Real time voltage information at bus number 1, 5 and 22 are provided to the corresponding voltage regulating devices connected at bus number 1, 5 and 22. So, overall what we wanted to focus that these devices do control the voltage at the respective buses like bus number 1, 22 and 5, but they do not really communicate among themselves to see what kind of scenario other buses do face. There are different voltage regulating devices, and the very common is OLTC. OLTC changes its step position if the voltage of the first bus vary within plus or minus 10% of its nominal value. That is, if the voltage is varying between 0.9 to 1.1, and then they can take action. If the voltage variation at the regulated bus of OLTC crosses the predefined dead band, if it crosses between 0.9 to 1.1 minimum as well as maximum, then the OLTC try to change its tap positions. Now, similarly, the DFIG and the DSTATCOM, what we have done, those are the additional devices have been placed to look into or to take care of the system reactive power scenario. So, a 1.1 megawatt rated DFIG based wind system is connected at bus number 22 through a 0.69 kV slash 12.66 kV step up transformer. A 0.8 MVA DSTATCOM is also attached at the same bus. Furthermore, a pair of switchable reactive load each rated with 0.4 megawatt and 0.2 MVAR also connected at bus number 22. So, these are the three things which has been additionally connected to my IEEE 33 bus system at bus number 22. Now, we also have included a DC microgrid at bus number 5, where at bus number 5 the DC microgrid is connected through 2 MVA rated DC AC converter. It includes a PV source of rating 1.8 megawatt operated at its MPPT with help of unidirectional DC-DC converter. A stack of lead acid batteries with capacity 0.4 megawatt is also connected at the same bus. A pair of switchable DC load rated with 1.7 megawatt is also connected at the same bus. Along with this, a pair of switchable AC loads with each of the rating 0.12 megawatt and 0.06 MVAR also connected at bus number 5. Apart from the change in load rating adopted in bus number 22 and 5, the rest of the parameter, as I mentioned earlier, are similar to IEEE 33 bus distribution system. Those parameters which has been chosen for this analysis need not be a fixed variable. Just for a case study, we have chosen this parameter, but you are very open to choose your own parameter, own settings and carry out the similar simulation. Now, in any system, we do have come across three different states. The first one is steady state, and then dynamic state, and finally your transient state. Now, what kind of reactive power and voltage scenario during all those states? First of all, if you consider the state number 1, where actually we say the steady state at which small loads are being switched on, the variation is not significant, a very minor change on your load, and the reactive power supplied by the fast acting converters which takes part in the contingency situation are less than 40% of their rated capacity or available rating. Whereas the voltage magnitude of the regulated buses are within 0.9 to 1.1. But if you move to a dynamic state where actually any sudden load changes will fall under the stage 2 category. The reactive power support required from the fast acting converters are more than 40% of their available capacity. During the steady state, it is below 40%, and during dynamic state, we expect it is to be more than 40% on their valuable rating. In order to build the reactive power reserve, the reactive power support of these devices are hard limited 40% of the limit. Okay, so we limit hard at 40%, whereas the bus voltages or the magnitudes are regulated between 0.9 to 1.1. The final one, which is very important, the transient state, when 3-phase to ground fault or 3-phase to ground temporary fault is triggered for a duration of 150 milliseconds, the voltage of the regulated bus certainly falls below 0.9 per unit, and hence the system enter into a transient state. Here the fast acting converters are allowed to inject reactive power up to their maximum capacity, as maximum as 100%. Now, if you look into these two different flow charts, the CVC schemes are not very new, they are very, very old and being practiced across the world. And whereas the conventional scheme, you can see that it is a simple algorithm, whereas in the proposed CVC scheme, what I am going to talk about today is slightly different, where we have taken care of the handling of different converters so that the overall performance of the system is being improved. And further, if you see what are the challenges with the existing CVC scheme. Now, the current limitations of the CVC scheme, coordinated voltage control schemes, given the importance for the speed of operation of devices only, because it really takes care or give importance to those devices who are fast, does not check for the availability of the devices for particular operating conditions. All the fast acting devices are considered for injecting reactive power simultaneously along with slow devices. So, what we do when it is from stage 1 or stage 2 or stage 3, all the reactive power injected devices are instructed to inject as maximum they can, and in that process the fast acting devices are always regularly participating in injecting reactive power, and the slow devices unfortunately may not be able to contribute by the time all the fast acting devices do contribute whatever measure contribution they can make. But that is not a good idea. In the proposed model, what we have suggested, utilize the devices more effectively. Even the OLTC, STATCOM, DFIZ, DC microgrid, all of them have to participate simultaneously, by which it improves the voltage profile of the system at large, it improves the fault right through capability of the devices, it also improves the transient conditions of the systems. Now, how it is being proposed here? The first stage, identifying the operating conditions of the grid. Based on the real time voltage information from the voltage regulating buses and the reactive power injected by the fast acting converters, a particular operating condition of the grid is identified. And then in the second stage, checking for the availability of the devices and assigning the master and slave role. So, who will act as a master and who will act as a slave depending upon the fast acting or slow acting devices. It is required to first check for the availability of the device for a particular operating condition before assigning any role to it. For example, OLTC and DC microgrid are used during steady state and dynamic state, whereas the wind generators and these STATCOMs are available throughout all the 3 states. Now, the final state, introducing the time delay in operation. For example, you want some slow device to be acted before the fast devices, then a delay in action on those fast devices can be incorporated, so that the slow devices can inject the reactive power, and further the fast acting devices can come to action. So, as an intentional time delay is inserted for all fast acting devices like WGSC and DC microgrid, DCMG converter along with the D-STATCOM, this ensure that the slow acting of OLTC would complete its action. So, as we discussed earlier, when all those fast acting devices come to action, then the slow acting devices may not be able to contribute much. So, please allow the slow devices like OLTC to act first, and then the fast devices can come and follow them. After which the fast acting devices are allowed to operate. The minimum delay time is calculated for each and every bus where the fast acting converters are connected. If the waiting period is less than this delay time, then the OLTC might not complete its action. And this is what the proposed CPC scheme, because most of the control schemes we have discussed in past. So, I am not taking a lot of time here, but as a whole you can see that this is basically DCSC bidirectional converter implemented with the proposed CPC scheme. And whereas we talk about actually the modeling for DC grid bus voltage, and this talk about the degenerate duty ratio for the bidirectional DC-DC converter of the battery, and the final one talking about the track MPPT of PV within DC microgrid. So, you can see different control algorithms or control schemes or the strategy being developed to execute the proposed case study. Now, in the result and discussion section, we will see what kind of outcome it is, because by adding a time delay and allowing all the devices to act in a different phase of time, not simultaneously, through which the slow devices do not contribute much, and hence with the proposed CBC scheme, we will see what kind of advantage of merit is being achieved. In order to validate the effectiveness of the proposed scheme, the system is tested under all the 3 operating states of the grid. The modified IEEE 33 bus distribution system is simulated in the real time digital simulator RTDS platform, and we have considered the grid rated voltage of 33 kV and frequency of 50 Hz, and the OLTC substation transformer of rating 10 MVA, primary voltage 33 kV, secondary voltage 12.66 kV, and the leakage reactance assumed to be 0.15 per unit. The D-STATCOM capacitors 2000 microfarads and DC link voltage of 600 volts, and wind speed considered to be 12 meter per second. The PV parameters of a DC microgrid is 100 ohm shunt resistance, series resistance of 0.5, short circuit current of 8.85 ampere, open circuit voltage of 37.6 volt, and solar irradiation of 1000, and number of panels in series and parallel 24 and 300. Power rating of each panel is 250 watt. The battery, lead acid battery of 400 volts and DC-DC converter of 0.5 megawatt. So, this is basically the system parameters being discussed before we proceed for the simulation. And during the RTDS simulation, we have seen this steady state operation for the PV output and for battery power, real power supplied by the DC microgrid, and reactive, similarly the reactive power supplied by the DC microgrid, and this is the DC load and this is the DC grid voltage parameters. So, during steady state operation of DC microgrid, all parameters being traced, whereas steady state and dynamic state operation of various devices at different AC bus of the distribution system, we have seen the real and reactive power load at bus number 5 and 22, whereas this is OLTC tap positions, how they are keep on changing, real power and reactive power by the DC microgrid, and reactive power supplied by the D-STATCOM, and real power and reactive power supplied by the wind generator. So, this all simulation results for your reference, and perhaps we can say the blue line represent the proposed CBC and red one is the existing CBC and the black one is without CBC. So, we compare if you do not have a CBC scheme, how does it behave, and if you have, based on the existing practice, how the scenario would be, and the proposed one. So, all three have been compared. The first, if you see the bus number 22 and this is at bus number 1 and bus number 5. So, this is how actually we have traced at different location. Bus number 22 where we had both D-STATCOM and wind generator, bus number 5 we had a microgrid, and bus number 1 we had a OLTC. Now, the state numbers 1 and 2, that is steady state and dynamic states, have been considered, and the voltage profile of regulated buses are being plotted. Whereas in this diagram, it is the state number 3, that is the transient state, which is very important from the state 1, and you can see the state 3 is being created at each and every bus. We can see the voltage profile of regulated buses. Now, the state 3 where we are during the transient state, the operation of voltage of regulated devices are being plotted. So, during the state 3, these are the bus positions and these are the device positions, OLTC, DC microgrid and wind generator and my D-STATCOM. RTD's simulation results where the voltage profile of 33 buses are being plotted, and with both steady state as well as dynamic state. So, the first one is during steady state and the second one is during dynamic states are being plotted. Now, let us see what exactly happened. During the state number 1, that is steady state conditions, how the DC microgrid operated or behaved. As per the proposed CBC, during this state, the OLTC and the DC microgrid converter act as a master, whereas the D-STATCOM and wind generator act as a slave. The results of the DC microgrid with proposed CBC scheme are shown in previous figures, where initially the DC microgrid is not feeding any real power to the utility. The power supplied by the PV is more than required by the DC load, and hence the battery enters into charging mode to regulate the DC grid voltage. At the interval T1, as you have seen, interval T1, DC microgrid starts feeding real power to the utility, and in this scenario the DC bus voltage regulation is achieved by supplying excess power from the DC microgrid to the utility grid. Now, during the interval for T2, the PV output is decreased due to fall in PV radiation, and hence the real power supply to the utility reduces to 0. During the interval T3, where there is a switching of additional DC load within the DC microgrid and the deficit power is supplied by the utility grid. Thus, in spite of all the switching dynamics, the controller of various converters of DC microgrid performs satisfactory. The DC grid voltage is regulated at 1200 volt during all modes. Now, in case of state 1 and 2, both steady state and dynamic state conditions, when we operation of various voltage regulating devices, the objective of the proposed CBC scheme during steady state condition is to increase the reactive power reserve of the D-STATCOM and the wind generator, and also to improve the voltage profile of overall distribution system. Now, in case of without CBC, all the voltage regulating devices rush towards regulating the voltage of their respective bus simultaneously without any concern of the reactive power reserve. Now, as we discussed, like during emergency, or if you do not have a proper CBC scheme, then they all try to help the system at their own locations, and perhaps without looking into how much reserve they carry with them. Though there is a best utilization of DC microgrid converter, the OLTC is poorly utilized with only one switching. In case of existing CVC scheme, though there is an additional switching of OLTC, the DC microgrid converter is poorly utilized because of all the fast acting converters along with OLTC are operated simultaneously. Once DC microgrid, D-STATCOM, wind generator reaches 40% of their rating, they are stopped from injecting reactive power further. The major problem is that they all act simultaneously. The moment they reach to their 40% capability, they have no more allowed to act. However, the proposed CBC scheme fully utilizes both OLTC and DC microgrid converter by providing an intentional time delay in operating the DC microgrid converters. Thus, the voltage profile of the regulated bus 5 is improved by an amount delta V as shown in the previous diagrams. Now, the voltage profile of the entire distribution system is improved in case of the proposed scheme that can easily be verified. The reactive power reserve of the D-STATCOM and the wind generator in the case of the proposed CBC scheme shows a significant increase by a maximum amount of delta QD of 40% and delta QW of 40%, both D-STATCOM as well as wind generator to 40% and by a minimum amount of 14% and 15.33% respectively compared to the existing CBC schemes. Furthermore, the reactive power reserve of the proposed CBC scheme is increased by a maximum amount of 59% and 56% by both D-STATCOM as well as wind generator and by a minimum amount of 19% and 15.33% respectively, opposed to without CBC scheme respectively by imparting time delay in their operation. Now, state number 2, dynamic state condition. In order to study the performance of proposed CBC scheme under dynamic state condition, load at bus number 5 and 22 are increased by 100%. So, to introduce a sudden load change, 100% load change have been introduced at both bus number 5 and 22 at instant T4. As a consequence, the voltage at these buses fall down from 1 per unit, due to which the D-STATCOM and WGSC increase the reactive power injection after passing through a delay period. Immediately after reaching 40% of their capacity, they are forcefully stopped from injecting reactive power in order to retain the same reactive power reserve so that the existing CBC schemes. However, the reactive power reserve of D-STATCOM and WGSC in case of the proposed CBC scheme is higher than that of without CBC by an amount 37.7% and 52% respectively for both the D-STATCOM and wind generators. In spite of additional switching of OLTC in the existing scheme, the voltage profile of the overall distribution system with proposed scheme is better and which has been observed in the previous pictures. Now, let us move to the transient state conditions. A 3-phase to ground fault introduced into the system for a duration of 150 milliseconds, due to which the voltage magnitude of the overall system falls below 0.9 per unit. Now, during this state, both WGSC and D-STATCOM play the master role and inject reactive power up to their maximum capacity. Now, it is reverse, not necessary. Those WGSC and D-STATCOM currently now act as a master and try to evacuate all the reactive power available to them. The OLTC and DC microgrid will be made slave and hence does not take part in the reactive power injection under transient state conditions. The DC microgrid is isolated from the utility grid and operate in an islanding mode and that feed the local DC loads. The gauge for deciding the efficiency of the control scheme is the ability by which the system recovers from the transient state at the earliest. So, the very interesting part here that we try to take advantage in the presence of DC microgrid along with other devices like D-STATCOM and the wind generator. And sometimes we force the OLTC to act in the beginning, but if it is emergency, then we do not allow OLTC to action in the initial stage. So the control study, the proposed CBC is certainly takes care of many other issues those have not been identified or addressed in case of the existing CBC. It can also be observed that as soon as the fault is cleared, the regulated bus starts to regain the voltage. However, due to the increase in reactive power reserve in case of proposed scheme, the system quickly reaches 0.9 per unit by a duration of delta T1 compared to the existing CBC scheme and delta 2 compared to the without CBC. So, the time of recovering got reduced with the proposed CBC scheme compared to the other schemes. Thus, the proposed CBC scheme needs less fault voltage recovery time in contrast to the existing schemes. Further, it can also be observed that after entering into steady state, the system reaches 1 per unit much faster in comparison to other schemes due to the better utilization of the DC microgrid converter and OLTC. In addition to this, the proposed scheme has better voltage regulation compared to existing schemes after entering into steady state from the transient state. The operation of various voltage regulating devices is displayed, from which it is evident that once the fault is cleared, the system rebuilds the reactive power reserve. And to conclude, what we wish to highlight, the proposed CBC, coordinated voltage control scheme, increases the reactive power reserve of the D-STATCOM as well as WGSC, and also improve the voltage profile of the overall distribution system during normal conditions. Furthermore, the proposed scheme is also targeted to reduce the post-fault voltage recovery period of the system. An intentional time delay is introduced for all the fast acting converter for achieving the set of objectives. The OLTC and DC microgrid converters are effectively utilized to improve the overall voltage profile of the distribution system during steady state and dynamic state conditions. It was observed that the proposed CBC scheme shows improved performance in comparison to the existing CBC schemes in terms of reduction in post-fault voltage recovery time. These are the following references can be used. This is a very interesting case study where you can see the benefits of having AC-DC smart grid together to address the voltage control scheme. Thank you.